Standing before the Great Pyramid of Giza today, even with all our modern engineering knowledge, it's difficult to comprehend how ancient builders accomplished such a feat. This massive structure, built around 2560 BCE, contains over 2 million limestone blocks, some weighing as much as 15 tons each. The precision is astounding. The base is level to within less than an inch across its 756-foot length, and the four sides are aligned almost perfectly with the cardinal directions. Ancient Egyptian engineers achieved this without computers, laser levels, or any of the sophisticated surveying equipment we take for granted today. The question that has fascinated historians and engineers for centuries is simple: how did they do it? The answer lies not in lost alien technology or mysterious vanished knowledge, but in human ingenuity, careful planning, and an understanding of basic physics that was far more sophisticated than we often credit ancient peoples with having. The construction of the Great Pyramid was directed by Pharaoh Khufu's chief architect, Humayunu, who understood fundamental principles that would be rediscovered and refined over millennia. The project began with site preparation and precise surveying. Egyptian engineers used the stars for astronomical alignment, tracking the rotation of circumpolar stars to establish true north. They used water-filled trenches to establish level baselines, allowing water to find its own level and marking the waterline on the trench walls. These simple but effective techniques gave them the precision they needed. The limestone blocks came from nearby quarries. Workers used copper tools and wooden wedges to split the stone. They would cut grooves in the rock face, drive wooden wedges into the grooves, then soak the wedges with water. As the wooden wedges absorbed water, they expanded with tremendous force, cracking the stone along predetermined lines. This allowed workers to extract massive blocks without explosives or power tools. Moving these blocks was perhaps the most challenging aspect of the entire project. Recent archaeological evidence has revealed much about Egyptian transport methods. Workers built wooden sledges that could be loaded with stone blocks. They would then pour water on the sand in front of the sledge, which had a remarkable effect. The water caused the sand grains to stick together, reducing friction by up to 50%. A team of workers could then pull the loaded sledge across the prepared surface with ropes. Experiments have shown that as few as 50 men could move a 2-ton block this way. Getting the blocks up the pyramid as it grew taller required ramps. The exact configuration of these ramps is still debated, but evidence suggests the Egyptians used a combination of straight ramps and spiral ramps that wound around the pyramid. These ramps were made of mud, brick and rubble, and they grew along with the pyramid itself. As each level was completed, the ramps were extended and raised. The limestone blocks were precisely fitted together without mortar. Egyptian masons would place blocks roughly, then trim them to fit perfectly using copper chisels and wooden mallets. They achieved joints so tight that you cannot fit a knife blade between the stones. This precision wasn't just aesthetic. It gave the pyramid structural integrity that has allowed it to survive 45 centuries of earthquakes, temperature changes, and the simple weight of time. The workforce was not enslaved as popular myth suggests. Recent discoveries of workers' villages near the pyramids show that the laborers were paid employees who received regular rations of bread, beer, and meat. While the Egyptians were masters of massive stone construction, the Inca Empire in South America developed different but equally impressive techniques for building in one of the most challenging environments on Earth. Machu Picchu, built around 1450 CE at an elevation of nearly 8,000 feet in the Peruvian Andes, demonstrates engineering brilliance adapted to extreme conditions. The site sits on a mountain ridge between two peaks, surrounded by steep cliffs and prone to heavy rainfall, earthquakes, and landslides. Building here required solving problems that would challenge modern engineers. The Inca approach began with understanding the landscape. They didn't fight against the mountain, they worked with it. The first challenge was drainage. Machu Picchu receives about 75 inches of rain annually, and without proper drainage, the entire site would have washed away or collapsed into mudslides. Inca engineers created a sophisticated drainage system with stone channels that ran throughout the complex, directing water away from buildings and preventing erosion. They built the city on a bed of crushed rock that acted as a massive drain, allowing water to percolate down through the site rather than accumulating. The stone construction at Machu Picchu is remarkable for a different reason than the pyramids. Instead of using mortar, the Inca developed a technique called ashlar masonry, where stones are cut so precisely that they fit together like three-dimensional puzzles. Some joints are so tight that they've remained perfectly fitted through 5 centuries of earthquakes. The Inca would quarry granite boulders, then shape them by repeatedly heating the rock with fire and cooling it rapidly with water, causing it to crack along natural fissure lines. Workers would then use river stones as hammer tools to pound the granite into the desired shape, a process requiring immense patience and skill. What makes Inca masonry even more impressive is that many stones are irregular polygons, not neat rectangular blocks. Each stone has a unique shape, fitting perfectly with all its neighbors. This technique actually makes the walls more earthquake-resistant. When the ground shakes, the irregular interlocking stones can shift slightly and then settle back into place, whereas regular blocks with mortar joints tend to crack and separate. Moving the stones was accomplished without wheels, which the Inca never developed. They used log rollers and ropes made from plant fibers that were incredibly strong. For vertical movement, they built ramps of earth and stone, similar to Egyptian techniques but adapted to mountain terrain. The Inca also used gravity cleverly. Rather than fighting against steep slopes, they sometimes shaped stones at higher elevations and then carefully controlled their descent down prepared channels. Across the ocean, Roman engineers were developing their own revolutionary construction techniques. The Romans' secret weapon was concrete, specifically a type of concrete that could set underwater and grow stronger over time. Roman concrete used volcanic ash called pozzolana, which when mixed with lime and seawater, underwent a chemical reaction that created a material of extraordinary durability. The Pantheon in Rome, completed in 126 CE, features a concrete dome that spans 142 feet and remains the world's largest unreinforced concrete dome nearly 2,000 years later. To build such a massive dome, Roman engineers had to solve multiple problems. First, they needed to reduce the weight of the structure. They did this by varying the concrete mixture and the thickness of the dome. The concrete at the base contains heavy aggregates like brick and travertine and is quite thick. As the dome rises, the concrete becomes lighter, using pumice as aggregate, and thinner. The Romans built the Pantheon dome using a sophisticated wooden framework called centering. This temporary structure supported the wet concrete until it hardened. The centering had to be extremely strong and precisely shaped. Once the concrete was poured and had begun to set, the wooden framework could be removed and reused for other projects. The interior of the dome is decorated with coffers, square indentations that serve both aesthetic and structural purposes. These coffers reduce the weight of the dome while actually making it stronger by creating a geometric pattern that distributes stress more effectively. Roman engineering extended far beyond individual buildings. Their aqueducts brought fresh water to cities from sources miles away, using gravity alone to maintain flow. The engineering required precise surveying to maintain a consistent gentle slope over distances of 50 miles or more. The Pont du Gard in France, built in the 1st century CE, is 3 stories tall and spans nearly 900 feet across a river valley. It was built without mortar, using precisely cut stones that support each other through the physics of the arch. In Asia, different cultures developed their own approaches to monumental construction. The temple complex of Angkor Wat in Cambodia, built in the 12th century, covers over 400 acres and required engineering solutions adapted to tropical conditions. The Khmer Empire constructed an elaborate hydraulic system that included reservoirs, canals, and moats. These waterworks served multiple purposes. They provided irrigation for rice cultivation, they symbolized the cosmic ocean in Hindu cosmology, and they helped stabilize the ground beneath massive stone structures. The temple itself is built from sandstone blocks, some weighing over a ton, transported from quarries 30 miles away. Khmer engineers moved these blocks by boat along specially constructed canals, then used elephants and human labor to position them. What united all these ancient building projects was careful planning and an understanding of materials and physics. Ancient engineers may not have had our mathematical formulations, but they understood leverage, friction, gravity, and stress through practical experience refined over generations. They used scale models to test designs and worked through trial and error, learning from failures. Many ancient construction sites show evidence of mistakes and corrections, proof that these builders were human and learned as they worked. The organizational challenge was as impressive as the technical one. Building megastructures required coordinating thousands of workers, managing supply chains for materials, maintaining tool production, and ensuring everyone was fed and housed. This required administrative systems, record-keeping, and leadership that could maintain focus on projects lasting decades. The Great Pyramid took an estimated 20 years to build. Angkor Wat required over 30 years of continuous work. These projects span generations of workers and multiple rulers. Ancient engineers also showed remarkable adaptability. When they encountered problems, they developed solutions. If one technique didn't work, they tried another. The construction of Gothic cathedrals in medieval Europe involved constant innovation as builders pushed stone construction to its limits, sometimes with catastrophic failures that informed future designs. The legacy of ancient megastructures isn't just the buildings themselves, but the knowledge and techniques they represent. Roman concrete formulations were lost for centuries and only recently have modern researchers understood how they worked. The water-resistant properties of Roman concrete are now being studied for application in modern marine construction. Ancient earthquake-resistant building techniques from Peru and Japan are informing modern seismic design.